So the first thing I want to talk to you about today is reactions and how they are created by the body, how they are controlled by the body. And so a lot of this is going to have to do with enzymes as well as the reactions themselves. The reactions that take place in the human body and in living systems are referred to as metabolism. And we've already outlined that a lot of metabolism is catabolism, breaking things down, and anabolism, building molecules. And so we also use that term to kind of collectively just refer to all the different reactions that take place in living systems. So certainly you've got the building side, the breakdown side. There's also a lot of neutralization processes as you're trying to adjust pH, and then transfer of energy and specific elements or nutrients. So the first type of reaction is called a synthesis reaction. This is where you build molecules, and these are associated with anabolism or anabolic processes. And there's two different ways that we typically portray these types of building reactions. One is that you have part A and part B, and they come together to form this compound. The other thing is that water is often a participant in these reactions. And so molecule A has a component of water on it, like maybe the hydroxyl group, and part B has a component of water on it, like a hydrogen. And so the water parts come together to form water, and the AB parts come together to form the molecule of interest. Looks something like this. Okay. And in a more real-world scenario, you might see something like two amino acids being joined together. So here are two amino acids. You should recognize these 5 basic pieces of the amino acid. And there are several places there where you could take a hydroxyl group, or you could take a hydrogen group, and you could join them together to form water. Typically, it is the hydroxyl group coming from the carboxyl, and one of the hydrogens coming off the amine group. And those are the ones that come together to form water. And that links these two amino acids together, forming a chain, and therefore a polypeptide. These reactions where you pull water from the reactants and form it as its own unique thing on the product side is referred to as dehydration synthesis. And this is one of the most common ways of producing molecules in the body and in living things. There's another way to look at this. This is the same reaction with two amino acids being hooked together by this process. The carboxyl group on the left here, the amine group on the right, and you can kind of see where they pull the OH and H to form water. Next kind of reaction is called decomposition reactions. These are involved in catabolic processes. Very often are energy-releasing reactions. And so a very similar set of processes can occur here, where you have one compound that gets broken down into its pieces. Or sometimes we use water to help us break apart those pieces. And when we do that, it's referred to as hydrolysis, to break with water. And you can see how the H2O kind of splits apart. This should look exactly opposite of what we saw in the synthesis reaction. Here's kind of a visual example of that. You can see the hydrogen and OH getting distributed there. Next reaction is a neutralization reaction. This is a situation where you have an acid and a base, and when they react with one another, they form two neutral substances, salt and water. So for example, a common one here is hydrochloric acid and sodium hydroxide can come together to form sodium chloride, plain old table salt, and water. You can see how the sodium and chlorine come together, and how the H and OH come together. Fourth and last kind that we'll deal with are called oxidation-reduction reactions. This is a place where electrons are getting transferred from one molecule to another molecule. That electron can represent energy. And so this isn't just about electron movement, it's about energy movement. And very often, if you watch closely, you'll see that hydrogens move around on the molecules involved in it. So let's look at one of the most important and kind of basic oxidation reduction reactions, which is glucose being burned with oxygen. This is how you guys get energy out of sugar molecule. And whenever you burn something, if you think back to, if you might have heard this said, that to build a fire, you need fuel. The sugar is our fuel. And you need oxygen in order to have a fire, to burn something. So when we do that, we get carbon dioxide, water, and ATP. Remember, that's our energy molecule, our energy storage molecule. So what happens here is that the hydrogens and the electrons that they represent get pulled off of glucose. Okay? And so as those hydrogens leave, they transfer their energy to the ATP molecule, and the hydrogens themselves join up with the oxygen to form water. Okay? You know that the energy is leaving the glucose molecule because the hydrogens are leaving that glucose molecule. And all that is left behind is CO2. CO2 is not a high energy molecule. There's not much left there. Very few bonds, only 3 atoms. And so the energy has shifted over to the ATPs. The hydrogens go to the oxygen to form water. A big part of most of these processes is that we have energy moving from one form to another form. The thing about energy is there's something called the law of conservation of energy, which says that you can't create energy and you can't destroy energy. You can shuffle it around all you want, but we're not really making anything. Okay? And so what these chemical reactions do typically is they rearrange molecules and rearrange energy to be most productive for us. That said, there's 2 major types of reactions. There's exergonic chemical reactions, where we are breaking bonds and releasing energy. And there are endergonic reactions, which need energy, and that's what we're collecting that energy for, so that we can complete those endergonic reactions, those energy-sucking reactions, so to speak. Okay? So everything about dehydration, synthesis, and hydrolysis reactions is very often about getting this energy shifted from one form into another form, particularly ATP as our favorite energy storage molecule. And just trying to be able to utilize that energy in the most efficient way possible. Now, not every chemical reaction that releases energy breaks bonds, and not every chemical reaction that requires energy makes bonds, but this is kind of the generality. And if you want to, you can associate these with anabolism and catabolism. Exergonic is usually catabolic, and endergonic is usually anabolic. In addition to this, we usually have long chains of chemical reactions where reaction A sets off reaction B, sets off reaction C, sets off D. And by doing that, by bringing these reactions together in that way, you can kind of have a trickle-down effect with the energy, where the energy for the first reaction can fuel the second reaction and the third reaction and work its way kind of down. You'll lose a little bit every time you shift to a new process, but it's more efficient than just utilizing that energy once and then letting it get back out into the environment. So enzymes are big role players, particularly in this efficient recycling of energy. And enzymes are of course, proteins. They're one of those important protein groups. They're really the way we regulate chemical reactions or control them. And without them, remember, we wouldn't be able to complete reactions at the speed of light. So this is really critical. The other thing that's great about enzymes is that while they are really critical to this process, they don't get broken down by the chemical reactions that they're involved in. So you can reuse them lots and lots of times. You can think of this as a chemical reaction maybe, that you and your textbook lead to knowledge about human biology. Now, I could just throw you and your textbook out into cyberspace and say, here you go, there's a test in 3 weeks, good luck. And hope that you learn chapters 1, 2, 3, and 5. all on your own. And online students very much have to do that a lot of times. The reason that you choose to come to a classroom is that you want a catalyst. You want something to make you able to learn faster and more efficiently and hopefully better. And so I play that role in the classroom. I'm your catalyst. I'm your enzyme. And so the reactants in this process are the same, you and the book, okay, as kind of the primary resources. And then there's me. I'm kind of off on the sideline. I'm involved in everybody's process, but I'm not really influenced heavily by your learning process. And what we get out of this, hopefully, is that you get that same amount of knowledge, but you get it faster and more efficiently because I'm involved in it. So I'm the enzyme to learn. When we start talking about really defining what enzymes are, I've come up with 4 words that I think are really critical to defining enzymes. Specific, recyclable, protein, catalyst. Specific is a word we use all the time and really don't think about what it means, I think. It means that there is one enzyme for one reaction, that there's a perfect match. If you need to do this reaction, you need this enzyme. No other enzyme can do it, and that enzyme can't act on any other reaction. I don't want to overuse this analogy in this section, but it's kind of like a lock and a key. There's only one there's only one key that can open this particular lock. That's a specific situation where there's one key to open the lock. Now, that key is also recyclable. So you can reuse the enzyme over and over again. That's a good deal. They're proteins. Might not seem like a particularly big deal, but remember that proteins have very specific shapes, and proteins have rules about pH and temperature and how that influences that folding, twisting nature of them. Lastly, they're catalysts, which means they speed things up. Now, there are other things that can speed up chemical reactions. In general, if you heat a chemical reaction, that will speed it up because the molecules involved in the chemical reactions run into each other much more frequently, and so there's more reaction. Concentration can increase chemical reaction speed because the more molecules there are, the more likely they are to run into each other, and so the more likely you are to have a reaction. Enzymes are different because it's not about how often the molecules come in contact. It's about the energy involved in the reaction. What makes enzymes different is that they lower something called activation energy. It's the energy to get started with a process. So I like to think that if I'm the enzyme in the learning process, the way that I lower your energy to get started learning biology is that I give you assignments like your pre-lecture questions, and I say, here, go read the book, and I'll give you points. So now you have a reason to get started. It makes it easier to want to crack that book open, because I know I never wanted to when I was a student. But if you're going to get points to crack that book open, maybe that's worthwhile. Okay? So I'm the enzyme, and I lower your activation energy. I make it easier to get started learning biology. Here are some examples of kind of what enzymes look like. You'll notice that they have kind of a slot where molecules fit into them. And so let's kind of name some of these parts here. The molecules that are put into a reaction with an enzyme are referred to as substrates. The molecules that you get out are called products. And then there is what we call the active site. This is where the substrate and the enzyme kind of connect together. So if you think about the lock and key concept, the key fits into the hole in the lock and rolls the little barrels and opens the lock, right? And so the key is the substrate and the lock is the enzyme, kind of, in this scenario. And they fit together in a very precise way, in a specific way. Because of that kind of thought process, there's been a explanation for how enzymes fit with their substrates called the lock and key theory, where the enzyme's the lock and the substrate's the key, and every chemical kind of corner has to fit just right, or the key and the lock can't work together. There's also an idea of what they call induced fit, which means that the lock and key maybe aren't perfectly matched together, but that the lock or enzyme kind of wraps around chemically that key and fits just right in the end. Not right out of the gate when you first insert the substrate, but it kind of fuses around that substrate after they come into contact. And because we're dealing with chemicals and not solid objects, that makes sense actually, because some of the parts of the enzyme are going to be attracted to some of the parts of the substrate, and it will kind of wrap itself around there to interact. So here's some imagery of this process. You see how the enzymes generally have this kind of slot for the substrates to fit into. They're shaped exactly the same. This is very much about shape. In the middle here we have a picture trying to show you about activation energy. You see how this is the chemical reaction, the blue ball, and it has to go up a little hill before it can come down and complete the reaction. The little hill that it goes up is this activation energy. It's the energy to get started. Once you get over that little hump, the reaction goes all by itself and speeds down the hill. But you got to climb those couple steps. You got to open the book, so to speak. So you can't read until you open the book, for example. There are two broad groups of enzymes. Not all enzymes fit into these two categories, but of course there would be catabolic and anabolic as two kind of main groups. Catabolic will break down a substrate. Anabolic will build a product from substrates. You can also think about these a little bit in terms of energy. Catabolic enzymes are generally releasing energy, and anabolic enzymes will be generally storing energy as they build those molecules. So there's a lot of direct linkages here. Not always, but often or frequently these things will be true. So one of the things you want to concern yourself is if enzymes are so critical to these processes and you need to control reactions, how do you control the enzymes? Well, one easy way, since they're proteins, would be to change the pH or temperature. Because when you change pH or temperature, it has the potential to denature or unfold that protein. The active site will lose its shape, and it won't be able to interact. The other way is something called allosteric sites. These are little on-off switches at locations other than the active site. It's away from the active site. And several different kinds of molecules fit into these places, particularly calcium, magnesium, and vitamins are things that generally we need in our diet because they're involved in allosteric sites. And some enzymes are enzymes that are normally off and have to be turned on. Some enzymes are normally on and have to be turned off. So, if this is a substance that turns on the enzyme, then it's referred to as an activator. If it's something that turns off the enzyme, it's referred to as an inhibitor. Last thing about enzymes here is that enzyme names are actually very predictable. They're kind of self-explanatory. One thing you'll find that all enzymes have in common is they have the ending ASE in their names. Do not confuse this with the sugar ending OSE. This is ASE. And I've got 5 major ones that we may encounter as we travel through human biology this semester. Isomerases and mutases are enzymes that rearrange molecules. You see the word isomer in there, so that should be a hint. Dehydrogenase, to remove hydrogens from a molecule. Synthases, build molecules. Kinases are the one that would be tricky because you can't really know what they mean. But kinase means to move, or kinesis is movement. And so this is to move phosphates in particular and typically to move energy. So you see kinases involved in energy transfer reactions very often. And lastly, we have polymerases. A polymer is a chain, so this is an enzyme that builds chains.